nevertheless, I'm going to psych myself up for this. Statistics. Yeah. All right. No, I'm excited. Today we're going to get done with, I'm going to give you an example of a mixture model, a really useful one that'll set up your homework, which is already up on the website. And I want to get started with the conceptual part of multi-level models. It gives us a little bit of a head start so we can do more quality time with the actual processing of them in the next 2 weeks. Because we only got 2 weeks left. It's going to be all multi-level models. So that's the agenda, and that is exciting to me. And I know to some of you too, you're like, when does the class begin? Right? Because you know some of this stuff, and you're like ready for the multi-level stuff. It's coming, but it's just I'm paving the way, and it's good to have a kind of methodological introduction to the more basic forms that underpin it. Okay.
Richard, a quick question about class logistics. Are we going to get any feedback on the homework before we get to the final? Just in case there's like mistakes that we keep doing, but we're not aware of.
The question was, you're going to get feedback on the homework. First answer, no. Second answer, well, there's a lot of you, and I do pretty detailed solution sets in that. But if any of you have particular concerns about something, like you do the comparisons between your solutions and the others, and you wondered, like, oh, is this a big deal? Then by all means contact me, and I'll try to fit you in. Lately, I know some of you have been trying to meet with me, and you know my calendar is incredibly impacted right now. But as February ends, it'll get better.
I think one of my questions might also relate to that would be if there's like pet peeves with how we're writing up our homeworks that are just really annoying, but we don't know it because we're not doing it.
That's probably not true because when Paul's been annoyed, he's been emailing people individually and saying, yo dog, don't do that anymore. So if you haven't received a grumpy Paul email, and I know some of you have, because it usually blind CCs me on but in general, you guys are doing formatting your homework's great. A lot of you are using Markdown, which is wonderful, and I haven't pushed that just because I wanted to reduce cognitive load. But I think Markdown's great because it self-documents for you later on. I mean, future you, there were some of you in my office hours earlier today, and I was telling you that future you will not know the things that current you does. So future you will want to go back in time and interview current you. And your notes, when you really document your model code, you do that for future you. You're doing future you a favor. So my model notes are like that for my published papers. Like there's just huge amounts of comments in them, and Markdown's nice because it sort of encourages that documentation. It makes it natural and freeform. So
is Markdown a thing, or is it just putting a pound and commenting?
Markdown's a thing. Well, that's a weird thing. Everything's a thing. But what's that? What's the word people from Philadelphia use for thing? I forget. What? Yeah, exactly. So it just means thing, right? Doesn't it? Anyway, so it's more than a thing. It's a system. It's a system of, anyway, Google it, Markdown, or Markdown, Google it. And I know there's some real pros of it in the class, so they might help you with it if you want. But I'm not pushing it on you necessarily, but it really does help increase your sanity reservoir sometimes. So it's a good idea. Questions?
Do you comment within Markdown better than just commenting
well, it makes a prettier document. So it's like you're writing. I mean, you can write a published paper in Markdown, and it has all the R code in it. It'll get executed as you rerun the document. So it's a great thing for helping document and replicate analyses. And when your colleagues
look at it,
then exactly. So it's a good system, and it's caught on really fast for that reason. And then when your colleagues want to know how you did it, you just send them the source file for the whole paper, and it's got all the R code in there. It's great. Yeah, that said, when you're running Markov chain models that take 8 days to sample, you don't put that in your Markdown. But so lately, I haven't been using it very much for that reason, because those are the models I've been running. I just waited 2 weeks for a model to finish mixing. But hey, there are exceptions to all workflows. Anyway, other questions before we get going here? I know the people who aren't in the class and have been watching the lectures love these weird stories at the beginning, right? People have babies and all kinds of stuff happens. Okay, what are we actually doing? Today, we're going to start with mixtures, and mixtures are also hybrid models. They have multiple stochastic processes. That is, you might think of them as likelihood functions. But the measurements that we have available have mixed those different processes together. I'll say this again. There are models that contain more than one likelihood function, so there's more than one stochastic process that's generating observations in the world. But our ability to measure those processes has produced a mixture of those processes, so we can't easily disentangle them just from the raw data. And I'll give you an example of how that happens. One of the most common cases in which this happens, and we'll inspect this next week, is the case of over-dispersed counts. So remember when I introduced count variables like the binomial and the Poisson, I said that for all counts, the variance scales with the mean. The greater the magnitude of it, the greater the variance in those counts. And that arises naturally from the maximum entropy nature of count data. When we observe counts in the real world and we make a count variable, typically that variance that we measure, even after conditioning on all the available predictors, is in excess of the expected variation given the mean. And that is often called over-dispersion. The counts are dispersed. They're wider than we'd expect if they were all from the same homogeneous process. And that's because nature has heterogeneous processes that generate variation underneath it. And you can very usefully model over-dispersion with mixture models. And the most classic ones are the beta binomial and gamma Poisson, and there are worked examples of those at the end of the count chapter. I'm not going to lecture on them, and I used to, and I'm not going to lecture on them partly because they're not nearly as useful as they used to be, because now we can do exactly the same thing with multi-level models, so I'd rather punt on that until next week and give you a multi-level example. That'll help broaden your understanding of what you can do with multi-level models, but multi-level models are our way to get heterogeneity into any level of the process that's generating the data. And that's what these sorts of mixtures are. Beta binomial and gamma Poisson used to be the only game in town because we didn't used to have Markov chains, so we couldn't fit arbitrary multi-level models. And the beta binomial and gamma Poisson have this conjugate structure that makes them easy. There are integrals that can be closed analytically, and then it's easy. I say something about this in the notes if you're interested. You'll come across people using them. They're still very useful models. They're sometimes pretty tricky to fit the data, though, and ironically, complicated multi-level models are easier to fit the data than those in my experience. It's a weird thing about them. So we're going to spend time instead in class on zero-inflated mixtures, which are incredibly common, and I think more common than people notice. So I want to draw your attention to them in a toy example, and then your homework has a parks management example. I call the homework problem parks and estimation. So here's the toy example in class, and this will be an example that also lets me re-emphasize to you the value of simulating dummy data to help you understand models. So we're gonna do the model forward and get data out of it, and then we're gonna do it backwards and get parameters back out of the data. This is a great thing when you're debugging your code to do, to reassure yourself that you have written the model right. So here's the setup. I want to imagine you're a monastery tycoon. You own a number of monasteries, and these things used to be monastery tycoons. Prior to the printing press, monasteries were the primary way that you got the printed word out to people. You had monks, and they toiled and copied manuscripts by hand, and they practiced their penmanship very well. And different monasteries have different productivities, and you're a monastery tycoon, so you need to figure out how hard your monks are working. Determines the market valuation of your monastery, among other things. So, monks copy manuscripts. The problem is they have cellars full of delicious cider, so they also get drunk and throw wild parties sometimes during the week. And this is all true from the historical period. So, the data we're going to be looking at, the outcome variable of interest that you have to evaluate the economic performance of some particular monastery of yours that you're interested in, is the number of manuscripts completed on each day. There's this logbook, and as manuscripts are completed and shipped out, someone writes down in a book how many were completed on that day. So it's a count. And this will be a Poisson variable, you might think, right? Because there are the manuscript, on many days, no manuscripts are completed because it takes a number of days by hand to complete a 400-page illuminated manuscript. It can take a while. So there are many days where none are completed. Some days you get like 4. That's like a day where everything lines up right. But there are lots of monks, many, many more monks working in the monastery than manuscripts get completed on a given day, because it takes much longer than a day to complete a manuscript. Make sense? So very large number of trials, that's monks working on manuscripts, and a very small probability of completion on any given day. Binomial shrinks to Poisson. Poisson density does good work here. The problem is there's a heterogeneity in the process because they're not working on every day. Some days the monastery kind of shuts down and drinks, and they go on a bender. And on those days, there are zeros. They don't produce any manuscripts. But even on days when they work, they sometimes produce zeros. So this is the kind of data that we call zero-inflated. There's more than one process that produces zeros in the data. And you can't tell just from the data. Or can you? And that's the thing we're going to look at. So let's break out the analytical structure of this a little bit. And this is called a zero-inflated Poisson process. And this is the most common, I think, zero-inflated model. You can also zero-inflate binomials or any counts. You can, I'll talk at the end about, there's a whole family of stuff called hurdles, which are related to this as well. There's a hidden state here generating the data, and that hidden state is whether the monks were drunk or sober on that day. You can think of this as whether they were partying or working. And so there's an initial probability. You can look at the diagram on the right-hand side of this slide. P of the time they drink. Right? And then you always observe a zero. Y is our outcome variable, our count, our Poisson count. 1 minus P of the time they work, but there's some chance that you get a zero even when they work. And then some chance you get a number greater than zero. So when you observe a number greater than zero, you know they weren't partying on that day. But when you observe a zero, you don't know. And our challenge is to estimate how much partying the monks are doing. And it turns out we can do it when we write down the likelihood in a principled way, following this diagram. So that's what we're going to do. We're going to construct a new likelihood function that is a mixture likelihood. There are two stochastic processes in it. The first is binomial. Are they partying or not? There's a chance P, they party. Conditional on not partying, there's a Poisson process that generates completed manuscripts. And what we observe is a mixture of those two things. And at the end, we've lost the partying dice, or coin flip for partying. Right? You can imagine the monks have a wooden coin. On one side is a big frothy stein. On the other side is a quill. And they flip it every morning. And the question is, what's the weighting on this coin? Right? Although I should say, some of you know this. Flipping a coin, it doesn't matter how heavy one side is. You can't bias a flip coin. You've got to spin it. Spin it, it'll be biased. But flipping it doesn't work. Because of how angular momentum works. It doesn't matter how heavy it is. Try it. Put a big wad of gum on the side of a quarter and flip it. It won't matter. We're going to build a new likelihood. Let me walk you through the idea. We're going to simulate this data later, and it's going to look like this. So I just want to foreshadow for you what the data looks like. Manuscripts completed across the horizontal, and just a count, the frequency on the vertical at each of those values over, I forget how many days I simulated this. It'll come out later in the script. What I've highlighted for you is what you wouldn't normally be able to see is that there are some number of zeros. In this case, all of the ones that are shaded in blue are the drunken zeros. Right? The zeros that arose from partying days. And normally, you wouldn't be able to distinguish them, but they arise from the part of the diagram that I put in the blue box over there on the right. Does this make some sense so far? So let's build this up now. We can derive the analytical form of the likelihood function for this. Now, I have, of course, written a function in the Rethinking library that already does this for you, but I want you, it's important to me for you guys to understand the magic here, right, or the lack of magic, whatever it is. The guts of the golem here are not that complicated, and these mixture likelihoods are really just cobbled together from the logic of your story about how the data are born. Remember, early on in the course I said a really pragmatic way to work towards Bayesian computation is you want to tell yourself a data story. Well, that's a generating story of the data. And if you can make that story into an algorithm, you can write it in backwards order, and you have a statistical model that can recover the parameters from the data generating process. And that psychological procedure of thinking about the data forward and then writing the model backwards nearly always works. It's a very powerful way to approach it. It takes some practice to get better at it. So this is an example. We're going to think about it going forward and think about writing down the likelihood function from it. So let's go forward for a second, and then we'll write down likelihoods, analytical likelihoods that give us the probabilities of zeros and non-zeros. So the first thing that happens is our binomial process. This is P of the time they drink, 1 minus P of the time they don't. So P of the time, we're guaranteed to observe a zero. 1 minus P of the time, there'll be some Poisson process that kicks in. That's the quills paper going. Some of the time, that Poisson process produces a zero, and it produces it e to the minus lambda of the time. You're asking, where does that come from? That's the Poisson likelihood function. So if you Google Poisson distribution, you go to the Wikipedia page, you will find the mathematical formulas for the Poisson distribution. And if you set the outcome to zero, it reduces to this really nice thing. It's just It's just e to the minus rate of the process. And that's the probability of a zero out of a Poisson process always. So that's where that comes from. Conditional on their working, the probability of a zero is e to the minus likelihood. And then there's some other probability. If you observe an n instead, the probability of it is that thing, which is just the Poisson likelihood. That's what that is. That's where does that come from? If you take the binomial likelihood and you take the limit as n goes to infinity and p goes to 1 over infinity, that's what you get. You get that thing. So now we can think about writing down conditional on observing a zero. There are two ways it can happen, and we have to account for them both. So now think about it this way. You've got your data set. There's some case where a zero has appeared. What's the likelihood of a zero? Let's account for all the pathways in this diagram by which a zero can arise, and we have to use them all in the probability expression. And you may remember from probability theory at the beginning of this course or in some former course that when things happen together in probability theory, we multiply them. And when things are alternatives, they happen separately, we add them. So we're going to have an addition in here because there are two pathways to get a zero. So there's an or that appears. So the first thing that can happen is p of the time they drink, and we're guaranteed to get a zero. So the probability of a zero conditional on these parameters p and lambda are p or, that's why we add, plus 1 minus p of the time. They don't drink, and the Poisson process produces a zero, which is e to the minus lambda. Make sense? Yeah? This is all probability theory is. It's just and or. Write down all the things that can happen, figure out all the ways they could happen, count up all the ways that any particular event can arise. That's all probability theory is. It's just counting. It's a compressed form of counting. Does this make sense so far? Next step, what if it's not a zero? Conditional on not observing a zero, the chance is 1 minus p, because we have to get down the right-hand side of this tree, times the probability of any value n greater than 0, which is that expression, lambda to the n times e to the minus lambda over n factorial. Make sense? So we get a likelihood function that has these two terms in it. Conditional on observing a zero, the likelihood is up there on the left-hand side of the slide. Conditional on observing something greater than 0, it's that thing over there. Notice that even though when you observe something greater than 0, you know it's a Poisson process, you still have to multiply it by 1 minus p because they worked and managed to produce some manuscripts. So there's a multiplication. Does it make sense? And I'm not expecting you guys this is not a course where I'm going to give you some new mixture situation and you have to derive the likelihood, although that would be fun for some of us, mainly me. But I'm not going to expect you to do that in this course. It's good to know something of the logic, and eventually in your careers you may have a case like this where you need to cobble this together. And I think all of you are capable of doing it yourself because I've seen you do harder things in this course than this. It's just that this is unfamiliar. And you haven't done it before. So I want to expose you so that you know it's within your powers to do things like this. It's not that hard. Like I said, you've done much harder things already. So, how do we express a zero-inflated Poisson model? Now there are two parameters that describe the zero-inflated Poisson distribution, which is a Poisson distribution salted with some extra zeros. Right? It's got a big excess of zeros. That's why it's called zero inflation. And there are two parameters that describe its shape. Unlike the ordinary Poisson, there's one parameter, lambda, which is the rate for the average number of events per unit time. And this is mixed with a binomial distribution, or a Bernoulli trial at the start. And its parameter is p. So the zero-inflated Poisson distribution is a function of both of those parameters. So we have two linear models now, if you so choose. You don't have to. You can just estimate p and lambda. But if you have predictors you'd like to make the probability of drinking and the rate of manuscript production conditional on, then you need two link functions and two linear models. And the linear models can be completely different from one another, and they have different parameters in them. It's up to you. They can. So the example I've given here, there are two different intercepts, two different beta coefficients, and then a common predictor, x, whatever that is, like how sunny it was outside, whether they decide to drink or not, or how much cider is in the cellar. X could be that. But they don't have to be. Given your background knowledge of the system, there can be different predictors in these different processes, right? It could be something completely different that determines whether they party or not, compared to how fast they produce manuscripts when they're working, right? Could easily be the case. You think about I had an older example where it was grad students producing manuscripts, and I thought that was too close to home. So, yeah, that's also zero-inflated. I have a data set on that. If you're curious sometime. Does this make sense? Yeah?
Why is the second one log instead of logic?
Good question. Why is the second one log? Because that's the Poisson rate, and what we want to do is constrain it to be positive. Lambda needs to be positive. So the customary link when you want to constrain a parameter to the positive reals is to use the log link. Because if you exponentiate that linear model, it's guaranteed to be positive. Yeah. So we're using the conventional links from the binomial model and the Poisson model. They're still in here, but both processes are in the same model now. Okay. So let's simulate some data now. And by the way, there's a whole bunch of classic paintings of drunken monks. It's really great. Go to Google image search sometime. Just put in drunken monk and hit image. Tons of great stuff. And it's not all Jackie Chan movies. Some of it is. I think it's very important as your models get more complicated and you start to feel yourself being nervous about your conceptualization of the model structure, to simulate data out of the process to make sure you understand what's implied. And if you can recover the parameter values from your simulation, at least get the neighborhood of them, then that guarantees that your model is working right and that you understand what the model implies generatively about the data. This is a great thing. And when you're developing new models, this is absolutely essential for new model types or fancy code. So for these models, I joked to you, I just finished a 2-week model fit. You can believe that I started it off this way. Made sure it worked on simulated data first before the 2-week run on real data, because I guarantee you I went through many rounds of bugs in my code before I knew it worked. And how did I assure myself it worked? Because I had fake data where I knew the truth getting in there. And you converge on it, and then you trust your software, and you can run around the real data. Does that make some sense? This is very important. The models in this class are mainly pretty simple, but still, simple's in the eye of the beholder. And you get something extra out of the forward simulation approach. So I'm going to show you that here because it's really simple. And it'll give you an example you can scaffold off of in later work. So we're going to simulate dummy data, I like to call it. We're going to recover the estimates, and hopefully this will increase understanding of the model. What we're not going to do in the example here, but I encourage you to try at home, is to try parameter combinations that are extreme. And you can see that sometimes you really can't recover the process because there are ceiling and floor effects in these nonlinear regressions, and that removes information from the data about process. If the processes push things in really extreme directions, you can't figure out. There'll be just a bunch of parameter values that are consistent with the data, and absent a psychic friend, you can't recover it. And that's important to know. Now, the nice thing about that is the Bayesian posterior will tell you that, right? It'll be wide over some range because it's telling you the relative number of ways that each parameter value could have generated the data conditional on the model, right? So it isn't going to lie to you and give you false precision, but you shouldn't expect to always be able to recover the data generating process in a nonlinear model. It's just the way the world is, right? This is called the generalized inverse problem. You might come across that in the physics literature. It's a cool fact about doing science, I think. It makes it fun. It does. It's because there's a problem to solve. You need to find another way of looking at the data, some other kind of data description on different scales, often to solve those problems. Okay, so let's simulate some manuscripts. So this code, I want to run through it real quick. And just so you guys understand how easy this can be, first we just define the probability of drinking. We define the fixed true parameter values of the process. The probability of drinking is 0.2, so on 20% of the days that monks drink, right? I'm not sure historically what it was like, but if I were a monk, I would drink a lot. That's all I can say. Yes.
So this is probably a silly question, but how do you get the 0.2? Like,
I just made it up.
oh, right.
You want to try, like I said, you try different values.
Okay, so you just kind of like plop in.
Yeah. Yeah, you try different values because you're validating your code and you're trying to understand the model. That makes sense. This is not a hypothesis that it was really 0.2, and you're not going to publish these data, right? This is about understanding it and making sure the code works. So I hesitate to say that value doesn't matter because, again, for extreme values, really high values near 1 and really low values near 0, you'll see that the estimation problem is a lot harder. It is. For point 2, it's pretty easy. I'm going to show you an example. But you make up the example because it's a form of intellectual play. That makes sense? It's not cheating, right? Unless you publish this, right? Which you definitely don't do, I think. I mean, this is kind of the... Anyway, no, I'm tempted to start talking about fraudsters, but I won't. I was going to say fraudsters usually, luckily, aren't sophisticated enough to know how to do this. And then they do things like everything's perfectly linear in their fake data. It's like, come on, people. It's like, give me a challenge here. And the data forensics community is like, whatever. You know, like that Dutch social psychologist that made everything like a perfect straight line or something. It was like, come on. You're not even trying to trick us. You know? Anyway, but, you know, if you work in SPSS, it's like, what is a random number generator, right? It's an issue. So it's fortunate. Anyway, you guys are honest, so I'm not worried. So N is, now there's like nervous giggling in the crowd. Right? Well, you're going to publish all your scripts, right? Everything will be audited, right? So you're the new generation where everything's open methods and replicable. Yeah? Yes, absolutely. I will haunt you if I follow up on your scripts in there. I will haunt you. A drunken Irish ghost following you into professorhood. All right, where was I? Sample 1 year of production. Rate of work. On average, 1 manuscript a day. That's the Poisson rate, right there. Yeah. We're going to do a whole year of simulations, just because. And then we simulate. First, the first stochastic process, the one that's latent in the real data that we don't get to observe. Right? We don't have data on this. You could imagine getting data on this, but as Monastery Tycoon, you only have that logbook. And the monks have tried to hide this data from you, that we're about to recover it. Because we were stats hotshots, and they didn't know that, right? So, do they drink or not? It's a binomial process with 1 trial, otherwise called a Bernoulli trial, and you just put probability of drink in there. Drink now holds a bunch of 0 and 1s, which indicate whether they got drunk on that day. Then we pass that drink variable right into our simulation of the Poisson distribution, and notice that formula looks like the likelihood that we wrote before. It's 1 minus the probability of drinking, whether they actually, now it indicates whether they really drank or not, times a random Poisson number, n of them, with an average value from rate underscore work. Y holds 0-inflated counts, 0-inflated Poisson counts. With me? Really all it is to it. Does this help you see what's actually being assumed? So now let's look at the model. This model's easier. I'm not going to put any predictors into it, but these are just linear models, so all your previous tricks, fine. You can put interactions in there, whatever you want to do. No guarantee that you can recover the parameter estimates you want, but sky's the limit, right? Let your science decide. And you put this into map exactly as you might expect. DZI plus is a likelihood function, a density function that I programmed into the rethinking package. There's a box in the notes where I do the dissection of it and show you what its guts look like in case you ever want to write your own likelihood function. There's a scaffold in there for you to see how it's done. It's not that hard. But it's one of those overthinking boxes that I say you don't need to read until the second time through the book, right? Okay. Does this make any questions about this? The only new thing is that DZI plus is there. Yeah. All right. When you look at the estimates, exactly as you might expect, here's just looking at the Précis output in the middle of the slide. We get an estimate. AP is the log odds of there being drunk, right? Drinking on any particular day. And it's minus 1.39. Let's call that minus 1.4. Now it's log odds. So to get it back on the probability scale, you plug it into logistic, right? So I do that down here in the bottom of the slide. Logistic of minus 1.39 is 0.1994, which is close to 0.2, which was the data generating process, right? There's a lot of days here. So with 365 days of data, you can recover the process really accurately. Same story. Now for lambda, AL is the log scale average manuscript production per day. It ends up being very close to 0.05. So we exponentiate it to get it back on the count scale because of log length. You use the inverse length. And that is nearly 1, which was what we assumed about the process, right? So it works. Make sense? Yeah, question?
About the inverse link going from your log scale to the probability scale, when we're plotting the results of the model, do you have to go from the log scale to the probability scale and then plot the probability of success?
From the logit scale to the probability scale,
right, yeah.
Or to plot the probability of success, yes, you got to undo the logit transform,
right.
So logistic it. But you could do things in log odds.
Right.
You can do that. It depends. So
that's like what we did in the book. In the book, right, with the pulling the levers, we were just looking at the probability in log odds. You
were looking at probability. Well, there's some graphs where we look at the parameter scale and it's on log odds. That's right. Then there are other graphs. The posterior prediction checks are all on probability scale. Okay. Right. Yeah. This is horoscopic advice time. So in a particular context, I could sit down with you and we could figure out what's most useful here. There are cases. I was collaborating with a lab in Lansing. They may be, hello ISIS if you're listening to this. They work on ticks, behavioral ecology of ticks. And they had this cool project that they pulled me in on because I'm a sucker for creepy things that suck blood out of mammals. But no, it was a cool stats problem. So it's about tick questing. So this is what they call it in the tick literature. Ticks climb up on things and they wait for warm objects to pass by, like joggers, and then they jump on them. And so there's this questing behavior where they crawl up on things, but they get desiccated really quickly, so they got to go back down into the leaf litter and chill for a while and get their moisture back. And so there's this questing behavior, and they're interested in it. And so they had a bunch of experiments, field trials with questing behavior of ticks that they measured. Most of the time, the ticks are in the leaf litter. So you want to estimate the probability that they're questing on any particular cross-section. It's really low. So on the probability scale, it's basically on the bottom axis always. But there are big differences across treatments on the log odds scale. And it has huge consequences for the system. Like probably a jogger gets Lyme disease. And so it's a cool problem where in that case, I looked at everything on the log odds scale because you could actually see differences. And they're very reliable differences. And ticks are savvy little things. Good, fancy little spiders. So, yeah, anyway, does that help?
Yeah.
Okay. All right, so yes, I think I'm done with this slide, right? You guys tell me. Yeah, I forgot where I was before I started thinking about ticks again. I'll wear my tick shirt next week. I had this tick shirt they gave me called Go for Blood. But anyway. So, other mixtures. So let me just review back to this. You can also do zero-inflated binomial, and there's a density in rethinking to do that as well. You can derive it the same way. It's just the Poisson gets swapped out with a binomial likelihood. It's the same idea. There's a whole bunch of hurdle models that combine some process that generates zeros with a process. If it isn't a failure, you get a continuous reading, some indication, like a gamma distribution or an exponential. So those are often called hurdle models. They arise a lot in biochemistry because you're trying to detect the concentration of something in a solution, and your assay doesn't work until the concentration is above a certain hurdle. So you get zero inflation because there are these low concentrations where it's there, and they all read exactly as zero because the assay just shows up as zero in those cases. This is a common, those of you who suffered in the bench sciences, you know what I'm talking about. I published a paper 2 years ago, I think, on human data where the hurdle model was useful because it was foraging trips. So guys go out hunting in the Paraguayan forest, and 60% of the time they bring back nothing. That's a zero harvest is what it's called. Sometimes they bring back a howler monkey, and then the record is the kilograms of meat that have been brought back. Right, so it's not a zero. You could call it a zero-inflated kilogram model, but it turned out to be a zero-inflated gamma model, which you can construct the same way. It just deals with the fact that there are two processes that are producing the outcome. Right, did you get anything, and then how big it is? Right, and there's two processes that go on there. Yeah.
So there are also two processes that produce an outcome. Let's say you just want to measure height of individuals. And you have, let's say, environmental processes like nutrition and strictly genetic processes like genes. And those are two processes, but you're saying they're not mixtures, and we've been fitting those look like regular linear models. So what's the
Yeah, so there's this issue of abstraction. When I say different processes, different stochastic processes at the level you're representing it. In the usual thing, right, we'll say, oh, there's a bunch of small additive effects, and they combine developmentally to produce height. And that's a mixture, sure, of effects, but we use the Gaussian because we think all these small things are adding. Or we just use the maximum entropy thing that we don't know anything about the process, but we do know it's essentially unconstrained and continuous, right? Does that help? Yeah. So, yeah, the vocabulary doesn't really do justice to all the choices you have to make in this stuff sometimes. Question?
I think I've seen it a number of times where like these type of models probably should be used, but just normal binomial over normal Poisson is being used. What is the consequence of not?
Great question. I should have made a big deal out of that in an earlier slide. So the question was, lots of times we see cases where models like this should be used, but people just use ordinary binomial or Poisson. What's the consequence? The consequence is that you will underestimate the rate. So for the monks, if you assume that they work every day and there's zero inflation, you'll get a lambda that's smaller, right? You'll underestimate their productivity when they actually decide to work, right? Because unconditional on whether they're drinking or not, their effective rate of production is low. And that's what you'd be estimating if you just treated it like a Poisson. But you're getting the wrong inference, right? Because if you could actually crack the whip and make them work every day, they'd be a lot more productive. Does that make sense?
Yeah.
So that can be a big deal. And your homework is meant to be a pragmatic, as I said, it's a park management data set that is about this. It's about fish extraction from a national park. It's exactly this problem. Not everybody goes to the park and actually tries to get fish. But you can't rely upon their testimony about that. And so it might help you think through it a little bit and get into it. But it's this issue of getting a more accurate measure of the actual rate of extraction. Yeah. Trina.
Just kind of to clarify on the genetic thing, if you knew something about the genetic process and how it was non-additive, like you knew it's this gene and it has this dominance relationship, then you could use this kind of model, right?
Maybe.
And then
I need to see. I'm sure, maybe. Again, I'm stuck in horoscopic land up here, right? And I'm the astrologer, statistical astrologer. I think often if you want to model development, you can do way better than just saying the outcome's Gaussian. Absolutely. And especially if you're, so I know I have some colleagues that work on C. elegans development, and the stuff that they do is scaffolded like these models. You have different stochastic processes, bootstrapping development up because they know when genes turn on, because we know everything about the genome of C. elegans, right? So definitely some hope to do stuff like this. If you know there's a gene that turns on early in ontogeny, and it can go different ways depending upon what happens, then that'll have consequences for the distribution of the later developmental processes. So yeah, I can imagine, I guess I just did, imagine a case like that, but I've never worked on anything like that. Yeah. Okay. Yes, and I said continuous mixtures are important. We're going to work on multi-level models to do those. Okay, remainder of today, I want to start